Hi everybody. Back with another problem. So similar to the last one, but another degree of difficulty. Here we have it cantilevered. All right, it's attached to the wall with no other supports. So the wall is providing both the vertical support and the moment. So we have the bar horizontal with this vertical component. We have 2 feet, 2 feet, 2 feet, 2 feet for all our dimensions. There is a 200-pound load at 2 feet from the wall, and there's a 100-pound load at a 30-degree angle with the horizontal at 4 feet from the wall up at the top of this vertical component. In addition, there's a 300 foot-pound applied moment at the on the piece. All right, so our first step is to draw a free body diagram, which is right underneath this. So free body diagram, you separate it from the part of interest from its supports, and you replace it with the reaction forces that support would supply. Here the wall would supply a force in the x direction, a force in the y direction, and a moment. Right. So that's really the only change going to the free body diagram. Right. Everything else is as it was on the actual diagram. Now you'll see I put directions on these, but you just assume something. It doesn't matter what direction it is, and you just be consistent with that when you're doing things, when you're doing your analysis. And then if you get a negative in the solution, that just means it's the opposite direction from what you assumed. So it's really not a problem as long as you carefully note in the beginning what you're assuming. All right, so the wall supplies the vertical shear forces and a moment that keeps the bar from twisting. All right, so now to find the reaction forces, I'm going to follow our same procedure. Sum of the forces in the x direction have to equal 0. So AX has to equal the x component of that 100-pound force. So that has to equal 100 cosine 30, because there's no other x force. Right? So I'm doing left forces equal right forces. So this immediately gives us AX equals 86.6 pounds. All right, now sum of the forces in the y direction. We're going to do, here we did left equals right. Here I'm going to do up equals down. All right, so up, we have AY plus 100 sine 30 equals 200. And again, we just have one variable here. So we just move our constants over here and add them up. And we get AY equals 150 pounds. Okay, now, to find that moment, we take the sum of the moments about point A. All right, and so didn't put that here, but this is going to be our point A. All right, now this is important. We're taking the sum of the moments about point A. My AX vector is a little bit off here. Both the AX and the AY vector go through point A. Right? They go through point A, so that means that they do not have a moment arm. Their moment arm is 0, so therefore they do not create a moment. So AX and AY do not create moments. All right, but the M here that we put in, this does not drop out. All right, that moment is a moment. It's not a force going through there. Somehow a moment is being applied. So moments are, and this is an important thing, the applied moments do not drop out. Moments are free vectors. Moments are free vectors, meaning you can't make it drop out. All right, it's trying to twist the entire piece, so it's applied to the whole part, not to just one specific location in the part. All right, so I'm going to do this doing counterclockwise moments equals clockwise moments. So counterclockwise, I get M plus 100 sine 30, that's the force, times a moment arm of 4 feet, plus 300 foot-pounds applied moment. That's going to equal 200 pounds times 2 feet plus 100 cosine 30, that's the force, acting at 2 feet. All right, one equation, one unknown. So M plus 200 plus 300 equals 400 plus 173. And so the moment equals 73 foot-pounds counterclockwise. Okay, so the fact that things came out positive means that we chose the right direction. We chose the direction that the reaction was in. Okay. Alrighty, so that's it. That's it for this one. We'll see you next time around.